Hi everybody, good morning. Welcome to lecture 7. So far in the course we have been discussing relational databases only. We've talked a lot about SQL, we've talked a lot about how data is modeled in a relational database. And now is the time to dedicate the last 2 lectures of this course to non-relational databases. Okay, let's get started. All right, so there's a reason that we have been discussing relational databases over 6 lectures and only dedicating 2 lectures to NoSQL databases. That's because many of the basic concepts are shared between relational and non-relational databases. And the thing is, the theory behind SQL and the particular way that SQL works is a little bit more complex and involved and takes more time to feel comfortable with and to understand and master. And the other factor is that still nowadays relational databases are still the most common databases that you might encounter, and all of them use the same standard, the same query language. And the thing is, a lot of non-relational databases also provide a language or an interface that looks a lot like SQL, because a lot of people are trained with SQL, so they prefer to use kind of similar interface or language to query other types of databases. So that's why we have been extensively talking about SQL so far. All right. So the whole idea about relational databases, or maybe the most important idea about relational databases, is that everything is not stored inside a single table or single data structure. We split the data between multiple tables, and by doing that, we want to ensure that referential integrity is enforced, and we also want to reduce redundancy. We also want to control database access, and so on and so forth. So these were the kind of things that we have discussed about relational databases, and the reason that we use this particular way to model data, to put data into several different tables. Okay, I think I mentioned in passing in one of the lectures that when a database designer starts to think about modeling particular data for a company, for an organization, they go through a process called normalization. And normalization is a systematic way to decide which attributes are going to be inside which tables, how they are connected, such that redundancy and duplication is minimized, and the database maintains its consistency and integrity in the best way possible. So this is a topic that is covered in classical database courses. However, we don't discuss that here because the goal here is not to train you to design relational databases. It's just important for you to know that this is the main step when a database designer, relational database designer, goes through when they want to start modeling their data in the form of a relational database. So basically thinking about what entities you have, what relationships you have, and what is the best way to put that information into several different tables such that the database stays in the best shape and form possible, such that storage is optimized, such that integrity is optimized, and all of that kind of constraints. I have included a link to a blog post here that you can check out if you're curious about normalization. But again, the most important idea is that we want to reduce redundancies by this process, and we want to maintain data integrity. Okay, so this is all very nice if we can actually minimize data redundancy and benefit from relational databases, but there is a price to pay, and that's the fact that we have to go through this process. We have to learn how to do it. We have to do significant upfront design and preparation. And the other thing is that once you have done that, once you have modeled your data, it's typically a little bit hard to change the structure of your data, to, for example, add one more column, a few more columns to one of the tables, because you have to be careful about a lot of stuff that goes on in your database. So it's not that easy. It takes a lot of time to design, and then it's relatively inflexible. Okay, so that's one thing. That is one great advantage of relational databases, but it also could be an impeding factor, especially for today's applications where we deal with large volumes of data, with data that we might not in advance know about their shape and form and the volume. Okay, that's one thing. The other major problem with relational databases is the fact that if we need to provide service to a larger user base, pretty much the only option that we have most of the time is what's called vertical scaling. It means that you have installed, for example, Postgres on a server. It's a very powerful server, but there's a limit to the storage space, to the amount of RAM, to the CPU's computation power. There's a limit. No matter how much you have paid for this system, if that system's maximum capacity is to service, let's say, 10,000 users, then as soon as you hit that, then you cannot go any further. Because even if you're willing to pay as much money as there's need to, there's still a limit on the hardware side. For example, CPU processing power nowadays goes as far as, like, let's say 6 gigahertz or 8 gigahertz, and that's the maximum. So beyond that, there's nothing to do. Or for RAM, let's say that you can have 256 gigabytes of RAM, 512, no matter how large that value is, because that's a constant maximum, you're gonna hit that maximum at some point. So that's one of the major downsides of relational databases. We have one single server, and we have limited capacity for that server. So this is what's called vertical scaling. You have, let's say you have 128 gigabytes of RAM, then you're dealing with more users, you're dealing with larger queries, more complex queries, then you just add 128 gigabytes of RAM on top of what you already have. So, but there's a limit to that. So this is called vertical scaling, making the existing server that you have more powerful and just improving the hardware that you already have in that system. That's called vertical scaling. It's also called scaling up in some contexts. Okay. However, there's another more popular option of horizontal scaling, which is also called scaling out. And that's through buying many cheap computers to store and process the data. However, in this case, the data is distributed among several different servers, not just one server. However, the great advantage here is that there is just no limit to the amount of data you can store, to the kind of to the complexity of the queries that you might run. There is literally no limit. And the other advantage is that you can use very cheap computers, but in large numbers, in order to achieve the capacity that you need for your user base. And that's a huge advantage. So this diagram illustrates that, vertical scaling, making the existing system more powerful by buying more RAM, more powerful CPU. However, with horizontal scaling, we just buy more computers with the same hardware. That's called horizontal scaling. Okay, questions so far? Yes. Overhead. What? Can you elaborate? What do you mean by that?
How does each server decide what it's going to do?
Oh yeah. So we're going to talk about that in a little bit. Yes. There's certainly a lot that has to go into that particular aspect of how to manage these multiple computers in an efficient way. Okay. Yes.
Once we're talking about horizontal scaling, the structure of our database is still relational, right?
So there are implementations of relational databases that support horizontal scaling, but this discussion kind of mostly applies to non-relational databases, and I'm going to discuss why. Okay. So this idea of horizontal scaling is the core idea of this new paradigm of distributed computing and storage systems. These days, when you use, I don't know if you have any experience using cloud services, you see that if you want to store your data and your data is very large, you can buy more servers, add more servers to your current existing service and stuff like that. And this whole thing is about is what's called horizontal scaling. The other thing that implements kind of similar idea is that you have multiple CPU cores on the same computer. And when you're trying to do some computations, then instead of having a more powerful CPU to finish the processing faster, you just distribute the job among multiple cores, multiple CPU cores or threads, and then that's called like parallel computing. Okay, so that's why over the past few years, at least I have seen that for example, CPU clock frequencies don't go higher anymore. I remember as a kid, the first computer I had was like Pentium 2, I guess, and then it had a 233 megahertz CPU with 16 megabytes of RAM, actually, and then over the years, each year there was a new CPU, like 400 megahertz, 600, 900, and I remember as far as 3.5 gigahertz, and I think the limit is kind of around 4, maybe 6 gigahertz these days, and that's like the ceiling. CPUs have not gotten more powerful, and that's exactly the reason, because we no longer prefer to do vertical scaling. We want to buy cheap computers, and we want to buy as many as we need. Okay. So why exactly do we need distribution models? That's because these days a lot of people are accessing their data or processing their data on cloud services. And in that case, one important factor for us is that we want to increase availability of our data. Suppose that we have one server, one relational database server here in Canada, and we want to provide service to like all users in the world. Then there's a problem with that because there's the network access. Suppose that someone wants to connect to our server from Australia, from China. So there's a huge latency and a lot of data that needs to be transferred over the network. So this is not really a viable option. However, if we use a distributed model of computing and storage, we can have multiple servers across the globe and then provide service to different users from a location that's much more closer to them, like in terms of physical distance. So basically what happens is that we kind of replicate or copy the data over multiple servers and then provide service to our users wherever they are. And this is not something that's supported by default in relational databases, and that can be a problem. The other thing is that, so with the advent of Internet of Things and with these days hardware and a lot of sensors that we have on many industrial scale devices like wind turbines and aircrafts and I mean, there are a lot of examples of these. So these sensors are generating terabytes of data let's say, per hour or per day, and it's no longer possible to store all that information, all that data in just one giant server. There's no way possible to do that. So this is what you might hear as big data. So it's no longer possible to have big data to store it's no longer possible to have big data and store it on just one single server. That's the problem. So when we're dealing with big data, scaling out or horizontal scaling is kind of pretty much the only option that we have. So what happens is that we have a gigantic amount of data, and we just split it into or divide it into multiple parts or sections, and then we store each part on one server or on a few servers. And then in this way, again, there is no limit as long as you have as many computers as needed. You can store as much data as needed on your computers. So you can see that there is certainly this need, and there has been this motivation to make distribution, storage, and computation possible over the past few years. All right. Yep, so we have discussed downsides of relational databases. Okay. So the solution to these problems that we have been discussing is what's called non-relational databases. These databases store data in a different format than relational databases. The data is not necessarily stored as tables, and there are advantages to this kind of treatment of data. And NoSQL, non-relational databases also are called NoSQL databases, meaning that they're non-SQL or not only SQL. So NoSQL, synonymous with non-relational databases. One important advantage of these databases is that you remember that in a relational database we have columns called attributes. We have certain requirements. The number of columns is fixed. The type of data that they can store is fixed, pretty much fixed. You can change them, but it's usually a very costly thing to do. And then this is one particular way that non-relational databases can be super advantageous, because the schema is usually flexible in these databases, meaning that if in one piece of data you have an attribute, you don't necessarily have to have the same attribute in another piece of data. Okay, if for a student you store name and let's say department, you can also for another student store a lot more information about that particular student, like a name, department, grades, courses that this person has taken, and so on. So you're not limited to the same schema for the entire data that you have. And this makes things much more flexible compared to relational databases. If at some point the structure of your data changes, that's no problem. You just keep on storing your data in your database, and your database is designed to handle cases like this. The other thing is that with non-relational databases, horizontal scaling is built in. So all of these non-relational databases that we're going to learn about in a bit, they are designed with this idea of horizontal scaling in mind, and they automatically take care of that for us. We don't need to do anything. As soon as the data grows in size and the queries become more complex, they just scale out as needed. Yes? Okay, so the question is, if we have horizontal scaling, we have multiple servers that store copies of data across the globe, and then if two users from two different parts of the world make change to the same part of the data, then how do we deal with the latency? What happens in that case? So the thing is that's a limitation of horizontal scaling that we have to deal with. So these databases, they are not consistent immediately, but eventually consistency is guaranteed. So you know that, okay, this user is making this change. That change may not be immediately reflected, but it is guaranteed that eventually the data will be consistent. And that depends upon like the number of users connected to the database, the network latency, and stuff like that. But eventually, that's going to happen. But that's a serious limitation, actually. Yeah. Yes?
Is there meaningful, so you said the schema is flexible and you can store different entities. Is that meaningfully different than storing like null values in a relational table? Like say like you store courses for student A and not for B, and you query courses for student B, would it throw an error? Would it return null?
Okay. So the question is, the fact that these databases are have a flexible schema, would this be equivalent to having a relational database and then having a bunch of columns and storing null values inside those columns? So the thing is, if you do that, you still have to think ahead what kind of columns you're going to have, which is something that we might not know in advance. And those null values, we still have to dedicate some parts of the memory or the storage in order to store those null values. Yeah, so we basically have to know, okay, here, instead of a number, we have a null value. So still, we are dedicating some storage space to that. Yeah, or at least some address. Yeah. Okay. So the next advantage is that in non-relational databases, because we adapt the structure of the database, of the data model to the data that we have, queries will be much faster. But that will be at the expense of redundancy. So because of the very same reason that I discussed, that these days commodity hardware is very cheap. You can buy a lot of storage for very cheap price, and I'll show you a graph later on that actually illustrates that. You're not really that much concerned about how much you pay for storage, if that's like a conventional storage, hard drives. So basically, if the data is duplicated because we're not using the most optimized relational structure, so be it. That's no problem. In this case, instead of using joins in order to bring data from multiple tables, we just store everything in the same place. Okay, because we can, because we don't care about the price anymore or the costs anymore, because things are very cheap these days. So we store everything in one place. Queries will be super fast. Yes?
How does horizontal scaling manage conflicts? Because like in a relational database, I would assume it just like goes through every request like one by one, whereas horizontally, you can have many requests at the same time. So how does it manage that? It's like writing software that wants to.
Okay, so the question is, how does a non-relational database deal with multiple requests that are like not, let's say, do not agree with each other, right? So because we have multiple servers and we can access different parts of data. So the thing is, we still have this idea of transactions, and this information is still kind of communicated between different servers. The way that it's actually implemented is way beyond the scope of this course, but this is something that the database management system actually takes care of, and it's a very important feature that the database has to have, the management system has to have. Yeah. But these are actually real concerns. So all of all of these advantages do not come like for free. We have to take care of a lot of stuff that we just took for granted in relational databases, because the only thing we dealt with was a single computer, single server, and everything was much easier. Now we have to be careful. Okay, if I'm changing this part of the database, did any other user also made that change, and I have to compare the times that those requests had been made and maybe reject some of the changes in favor of some others. We have to manage that. But, okay. So, to recap, again, the data model is flexible, horizontal scaling is built in, and queries are fast in these types of databases. Okay, so this is the graph that I was talking about. So suppose if we were discussing this in 1980s, then the cost of 1 megabyte of storage space would be as much as $2,000 per megabyte. And in those days, it was really important that you could squeeze out as much optimization as you could from the database structure. So relational databases were super important. You really wanted to avoid redundancy. However, look at the cost of storage these days. It's just almost nothing. So we really no longer care about how much we spend on that storage. We can use non-relational databases and in favor of having fast queries and being able to store the kind of data that we weren't able to before. Okay. Yes?
By that, do you mean each server will have the entire copy?
That's a great question. So not necessarily. Each server might contain several copies, but not the entire copy of the entire database. Right. Yeah. Yeah. So I'll get to that in a bit. So these have their own kind of terminology of how this is done. So let me, I think, or maybe I discussed it. Okay. So the thing is, there are two concepts attached to non-relational databases, at least for the database management system that we're going to discuss here. One concept is replication. So you replicate the data or copy the data over multiple servers in order to increase availability. That's just for availability. The other idea is the idea of sharding, like when you break glass and that breaks into multiple pieces. So you have a huge amount of data and you just divide it across multiple servers. So these two things can happen simultaneously. You might have sharding as well as replication. But when sharding happens, usually you no longer store an exact copy of the entire database on all of the servers. You might store, let's say, 3 copies of different parts of the database, of 3 different shards, but not the entire database. Yeah, that's like. Oh, no. It does actually increase the storage capacity because we don't store an entire copy, just a part of that. If we were to store a copy of the entire database, then you're right. We're still limited to how much information we can store in just one server. But right now, we divide the data into several different pieces, and we just store a bit of that on each server. The total sum is still the same as... yes. Okay, so again, replication is different from sharding, that's right. Yeah, so if you have replication, then you have copies. If you don't, then sharding would be the same as yes. So in case you're not dealing with big data, then sharding will not give you any advantage. Basically, you're right. Pardon me? Sorry, I can't hear you. Yes, right. That's right. Yeah. Okay. Guess we have to move a bit more quicker here. All right, two important points here. One is that NoSQL databases are also capable of storing relationship data, but the thing is they do it in a different way. It doesn't mean that as soon as we have non-relational databases, then relationships just disappear. It's not like that. We can still store relational data, but in a different way. And we also learned about ACID properties. Does anyone remember what those letters stand for? Yeah, so atomicity, consistency, isolation, and durability, the properties that kind of make us sure that changes that we want to happen together will happen together. And the thing is the database stays consistent. Multiple users can access the database without worrying about the fact that they might their processes might interfere with each other. And finally, you're sure that when the database tells you that the change has been made, even if there is a failure, you can rest assured that your change will eventually be recorded in the database. So non-relational databases used to be not ACID compliant entirely because of the nature of their structure. However, nowadays, most of them also support ACID at the expense of some more complicated processing. So basically, you have that option if you want to use that. Okay, so last thing here, in contrast to relational databases where we had this SQL language that was pretty much the same between different implementations, with NoSQL databases, then their query languages could be quite different. So each database management system has its own query language. Some of them actually use a language that looks a lot like SQL, and some of them, like the database management system that we're going to use, its query language is entirely different. All right. So just a quick overview of the different types of non-relational databases that are in existence today. The first type is simple key-value databases, which consist only of key-value pairs. We have a key and then a bunch of data associated with that key. These databases are best suited for applications where you kind of only refer back to that data or query the data based on the key, not based on data. So when you have that kind of data, then this is an optimized way of storing that information. And an example is Amazon DynamoDB. You're going to learn about these services in your 525 course, your web and cloud computing, I guess. We also have document-based databases, like the one that we're going to be discussing, MongoDB, which simply consists of data structures called documents that look like JSON documents. So a bunch of data stored as key value pairs, but the values could also have their nested substructures, which gives us a lot of flexibility in terms of how we can store our data. These databases are great for querying either by keys or by data, and we'll see that later on. We also have graph databases. For example, for an application like Facebook or Twitter, these databases focus on the relationship between data, and they're optimized for searching connections between the different entities. They have relatively few applications, so they usually are an added functionality of the existing database management systems. Examples, the most famous one is Neo4j and OrientDB. We also have another type of database management system which use a column-oriented data structure. A prominent example is Google Bigtable and Cassandra. These databases are kind of optimized for operations that happen in a column-wise manner. So, for example, if you remember, in Pandas, we do, let's say, a sum of the values inside of one column, and we specify the axis to be 1. So you know that operation Actually, not in pandas. In NumPy, it takes a lot of time because the data in a column is not stored side by side in a contiguous way. So you know that if we want to do that, we have to store our data a little bit differently if you want to optimize for that kind of operation. This is kind of the same idea here. With column-oriented data, the focus is on aggregating operations on columns. And these are usually used for in warehouse data and usually for data analytics. Okay, so I guess we can take our break right now. But next, we're going to discuss MongoDB, our non-relational database of choice. So let's take a break of 5 minutes. We'll be back at 8:42. All right, we're back. So one thing I forgot to tell you is that if you're curious about non-relational databases in general, like the basic fundamental concepts, so this RDBMS, this DBMS, this database management system that we're going to be learning about is called MongoDB. And I think it's a very good idea to check out its documentation because it's one of a kind. It's really, really well designed, and you can find a whole lot of information on different topics. They also have their own courses for different levels of NoSQL database usage. I really strongly suggest that you check the documentations out. It's one of the best that I have ever seen. Very, very clear. It contains comprehensive information, tutorials about pretty much anything you want to know about non-relational databases, especially about MongoDB. So they explain a lot of this stuff, like how sharding occurs, how replication occurs, how do they manage queries across distributed servers, how they manage that, and all those kinds of information, among others. Okay, so the database management system that we learn about here in this course is called MongoDB. I chose this one because this is the most commonly used non-relational database, the most popular one. This is cross-platform, open source, and super fast. It supports all of the functionalities that we have discussed so far, horizontal scaling, and all of that. Okay. So MongoDB is based on JSON-like documents. I don't know if you know what JSON documents are. Okay, so I'll show you an example later on, but basically that's what they store. They just store documents with a structure that looks like JSON. So we have key-value pairs inside of each document, and then the keys are just keys, and then the values could also be nested subdocuments. I'll show you examples later on. So yeah, again, native replication and sharding is built in. Automatic scaling and load balancing is there in MongoDB. Multiple programming language support is also there. It works with Python, C++, C, whatever language you're using. And it also has a very powerful query language. Okay, who uses MongoDB? Pretty much everyone. Google, eBay, Craigslist, Toyota, Forbes, everybody. So don't need to advertise for them. Okay, so this is what a JSON document looks like. So we have the keys, and then we have properties for those keys, or information stored for those keys. For example, here we have this name key, and then inside of that name key we have data stored as first and last, and for those keys we also have some information stored for them, and then we also have other attributes. So you can kind of think of this structure, if you want to make an analogy with a table, you could say that these keys would represent, loosely, they would represent columns in a table. So for each column, for example, you might have a column called name and contribs, awards, and stuff like that. However, in a relational database, in a table, you cannot have these nested subdocuments, these nested substructures, which is one of the main strong points about non-relational databases. You can store data structures that look as complex as something that we can see here, and even much more complex than this, with relative ease, and query that data with relative ease. Okay, forgot to say that JSON stands for JavaScript Object Notation. It originates from the JavaScript language, and then it has widespread use across many different applications, not just JavaScript. All right. So in MongoDB, instead of storing data in plain JSON format, what they do is that they take the data and they use what's called a BSON format, binary JSON. So instead of storing data as text, because a JSON document is just text, we don't want to do that because storing data as text is is very inefficient. It takes a lot of space. We don't really want that because that's a database concern we've learned about. And JSON doesn't really support different data types. It's just text. It doesn't understand anything beyond text. So with BSON, it's binary. It's like a dictionary or something like that you store in Python. Everything is binary. And that's like zeros and ones. That's a property that we like. The other thing is that text parsing in JSON is, because it's text parsing is very slow, so the kind of querying that data would be very slow if we just based our database on JSON documents. So we use BSON, binary JSON. Okay, so I told you that MongoDB stores data inside of these documents. Each document looks like a JSON document, and we call a collection of these documents simply a collection. So again, if we make an analogy with relational databases, a collection will be similar to a table. And the documents will be similar to each row in a table, right? Each row stores information about an entity. Here, each document stores information about an entity. A collection of rows create a table or comprise a table. Here, a collection of documents creates what we call simply a collection. Okay. Again, a diagram showing the structure of documents in MongoDB. Just like relational databases, we call these attributes, we call them fields, and then those values stored for them simply as values. So each document contains field value pairs. There is a field name called _ID for each document, which acts as the primary key, which uniquely identifies each document in our database. And MongoDB automatically assigns that at the time of document insertion, whether or not you specify. If you specify that it's going to use the value that you provide, it has to be unique. Otherwise, it's going to assign a value automatically. And finally, the maximum size of a BSON document is 16 megabytes, which for one single document, it's a huge amount of space, so you don't need to worry about any space constraints. Okay, so if you want to use MongoDB, you can follow the same process as Postgres. You can go to MongoDB's website, download the application, install that on your system, and then it will create a server running in the background that will answer to your queries and works pretty much in the same way as Postgres does. If you want to use MongoDB on a server, the steps will be the same. You have to log into the server, download MongoDB, install that, configure that, and everything that goes with it. However, MongoDB has provided a service called MongoDB Atlas, and then in Atlas, you don't have to do any of that configurations. You just pick your service, the kind of server that you like, you specify the version of MongoDB that you want, and it just configures it automatically for you without requiring you to touch anything, basically. It gives you a ready-to-go server. So that's what MongoDB Atlas is, and that's what I want you to use it, because you don't need local installation of MongoDB. You don't actually need to install MongoDB anywhere. You just set up your server on MongoDB Atlas and connect to it remotely. So that's the kind of recommended way. However, if you have trouble using MongoDB Atlas, the remote server, I have also provided instructions on the Slack channel that you can follow to install a local instance and then load your local database with your local database management system with the databases that we use for this course. So let me show you what this actually looks like. So this is MongoDB Atlas. If you sign up for an account, this screen will be what you will be seeing. And then once you're here, I have already set up my own cluster here. This is why you see this little window here. However, when you start using this, you're gonna see something like this. So what we're gonna use is this shared cluster, because typically these services are paid services. We have to pay for them. It doesn't come for free. However, with the share service, there is a free tier for learning about using MongoDB. You can choose your region, your type of server that you need, AWS, Google Cloud, choose the region that you want, and then finally choose the version. That's not really too important. And then finally click on Create Cluster. Once you do this, it takes a few minutes for the server to fire up, and then you'll have your own dedicated server that you can connect to and store information on. I'm not going to do that here, but you can follow the steps and have your own cluster set up. And once you do that, this is your cluster, your server. And then what I want you to do is to click on this load sample data sets. And these are the data sets that we're going to be using for the lectures and labs. Yes?
How long does that loading take?
Typically 10 minutes, about 10 minutes, but it depends on how busy the servers are at this particular region that you have your cluster set up in. Pardon me?
Mine's been down.
Yeah. I mean, last year, we had like a few hours of time because it depends on how busy the servers are. Okay, so once you do this, your database becomes loaded, and when you do browse collections, this is an instance of when it doesn't work. Okay, let me refresh that. All right. So you can see these are the databases that I have. For example, sample mflix, information about movies, and you can see here I have different collections. This is the database. These are the collections, and inside of each collection, we have all these documents that you can see over here. Okay, so this is what it looks like and what you can expect. So these are the documents. If I zoom in, you can see, let's say, for each movie, the awards, the writers, IMDb ratings, the year it was produced, and stuff like that. So you can check that out later once you have set up your cluster. But this is basically how it looks like. Okay, so this is the cluster setup. You can follow the steps, set up your cluster, or set up a local instance of your database. If you want to set up a local instance, you simply follow the steps that I have posted here. Install MongoDB on your computer. Pull the changes from the course repo. Okay? And then once you have done that, you navigate to the folder, to the repo folder on your computer, and you simply run this command, mongo restore archive, followed by the name of the file that you want to restore. And once you do that, it basically just create a similar instance of the databases on your own computer. And in that case, you don't have to wait for the remote server or deal with problems of latency or anything like that. All right. Okay. So that's about it for MongoDB Atlas. Now let me tell you about different interfaces that we can use in order to connect to a MongoDB server. The first way is using MongoDB shell, which is similar to pSQL that we had in Postgres. We're not going to be using that in this course. It's not really required. But I'm going to show you maybe a couple of examples of how that works. It's just a command line interface. You run commands there, you get the results there. Nothing really too fancy. However, just similar to pgadmin, we have a GUI, a graphical user interface from MongoDB, which is called MongoDB Compass. And again, this is something you have to go to the MongoDB website and download and install on your own computer. And this gives you an interface similar to pgadmin, actually much nicer. But it gives you basically a graphical user interface to write your queries, retrieve documents, do analysis, and stuff like that. On top of that, you also have MongoDB's Python driver. This is similar to PsychoPG2, which was Postgres's driver for Python. So it's just a package that is installed in your current environment, and you load your username, password, host data, everything like that. And then once you do that, you can connect to your database through your Python runtime or environments. Okay, so let me show you. Let me show you the MongoDB the Compass interface for a second here. Okay. So this is basically what it looks like. This is the Compass application. So you can see I have my local instance running. I have also my Atlas account set up. So I'm gonna choose this Atlas account. In order to connect to either Atlas account local data or local instance, what you have to do is to provide a URI, which is basically the information about the host address, your password, your username, the port that you're using, all in a compact form. How can you get that information? Very simple. If you go here, here in the, on this screen, if you click on connect, it will give you exact instructions to either connect using Compass, based on the version that you have, or, for example, connecting using Python. It gives you the exact code to do that, which is very nice. So here I'm going to use Compass. It gives me that string that I need to copy and paste into my Compass application in order to connect to the remote database. So here, the only thing that you need to fill out is this password field, okay? And once I have that, I can take this, copy that here. For example, if I do edit connection, it will unfreeze this box and I can enter my connection string. And once I do that, I can connect to my database. As you can see, I have all of these sample databases loaded on my cluster, and I can access them. For example, this mflix. You can see these are the collections that we have. Suppose that I click on this movie collection, and here we are. So this is one document that I can see here. This is another document, and then so on and so forth. And there are around 23,000 documents over here. So this is just to show you what the interface actually looks like, what a document inside of a MongoDB database looks like. Okay, there is one other step that you have to go through if you want to connect to the cluster. It is also explained in the link that I have provided, so you have to follow all of the steps, and that's you have to set up database access, meaning that you have to set up a username and password, which I have already done, and you also have to set up network access. So 0000 means that you can connect to the database from anywhere with any IP that you have from any network that you like. So those are two things that you have to do. It's mentioned in the link that I have provided. Okay? So network access has to be set up 0000 in order to connect from anywhere, and database access, you have to define a username and password for yourself. If you're connecting using your local instance, by default, there is no username, there's no password. You don't need to use a username or password. Okay. So that's about it. So let me load this credentials information. Client, this is how we create the connection objects, very much similar to PsychoPG2. And now let's discuss the MongoDB's query language called MQL for a bit. Okay. So in each of these sections, I have provided the ways to do that particular action either through Compass, through Mongo Shell, and through PyMongo. You don't need to really care about Mongo Shell. You only care about Compass and PyMongo. So it's just there as an FYI. Okay, so this is how we can access a particular database inside our database instance. For example, here I'm trying to access a database called MyDB, and I access it like I access keys of a dictionary, values of a dictionary, and this gives you the object. Hey, this is the object, this is the connection that you've set up, and these are the properties. And then that gives you a cursor object, similar to PsychoPG, and then there are certain methods associated with that client object. For example, you can do client.list database names. These are the databases that I have in my remote instance. And you can also access particular collections, again using this dictionary notation inside of Python. For example, here, if I access the sample mflix database and then do list collection names, I see the collection names inside of that particular database. Okay, just a bunch of syntax, nothing really special here. Okay. And now comes the more interesting part. So in order to query documents in MongoDB, we use this find method in PyMongo and a similar syntax in Compass. So suppose that here I want to find documents that have this value, this string Titanic, as the title of the movie. So the way that I can do this is using the client object, I refer to the database that I want to retrieve data from, and then the collection that I want to retrieve data from, and then apply this find command. And finally, I have to provide a filter. So remember that in MongoDB, everything is like a JSON document. Even the query that we create also looks like a JSON document. So here, this filter means I want to return documents for which the value of the title field is equal to Titanic. That's the query itself. And if I run this, it gives me a cursor, a Python generator. It doesn't give me the actual data. Just like PsychoPG2, I have to loop over that object in order to retrieve the data. So the way that I can do this, either because it's a generator, I can either do next, and here is the document. So you can see the plot, genre, runtime, rated, all of that information. It's actually a large document, so you can check out the entire thing in a text editor in VS Code. Okay. The other way is to basically pass that thing through the list function in order to materialize that. So that's the entire collection of documents returned based on that query. Okay, so the important part here is really not this part. This is just how we connect to the client and go to the specific to a specific database and collection. This is the most important part, the query part. Okay. All right, so let's do the same thing in MongoDB Compass, just to show you how it works. So here, I am in the same database, and I click on the same collection, movies, and then here it says filter. So I can type a query right here, open, close curly braces, and then do title, and then Titanic. Okay, when I do that, it finds 3 documents, as you can see here. So these are the 3 documents. Okay. Basically, we have run a query. Inside of Compass, we don't really need to use those quotation marks. We can just run it simply like that. For the value, I'm not sure, but for the, yeah, it works both ways. Okay. All right. So you can see that we can do the same thing in Compass. It's a little bit more interesting to work with compared to Python, but eventually if we're working with data, we probably need to retrieve the data from our Python runtime. And what you see here is MongoDB shell, and it's similar to pSQL. For example, I can run a command like this, show DBs. This is a particular command for MongoDB shell. It shows me the databases that I have, and we can also query documents right from this CLI, but I'm not going to do that. This is just to show you that this is also another option available. Okay, let's move on. So if we have a filter, an empty filter like that, it will return every document that we have in a collection. Okay, There is also another method that might be helpful that is called find_1 in PyMongo. Regardless of how many documents you have, it just returns one document. It might be helpful in situations that you just want to check out what your documents look like. Okay, questions so far? Yes?
Is there a specific order in which documents are stored? I know in relational databases, there's an order that's like preserved. So in this case, it's what was preserved.
Oh, the order of the documents. So yeah, the thing is, the order of the documents is based on insertion order by default, as far as I remember, based on insertion order. But again, this is, I don't know if it's really reliable, if it stays that way always. I'm not sure about that. But again, it's probably a better idea to use sorting if you really want a particular order in which documents should be returned, similar to relational databases. Yeah, but you can check out the documentation to see if that insertion order will be always preserved or not. Okay, any other questions? Yes?
How do we do calculations once we're making a query?
Okay, so how can we do calculations when we write a query? We'll learn about that. So what kind of calculations do you mean?
The type of calculation we're doing in select once we're doing severe.
Like multiplying a Yeah, we'll learn about that in the next lecture. That's mostly the more kind of advanced stuff that we will be discussing. Yeah. Okay, so in SQL, in the select statement, we could pick different columns based on what we wanted to do. We didn't need to return everything all at once, and you can see that our query returns a whole bunch of things that we might not need. So in SQL, that operation is called projection, when you just return a particular column from your table. And projection in MongoDB is done in a very simple way. The only thing that you need to do is that, so you provide the filter, and then in order to return only certain attributes, you just have these key value pairs. For example, title 1 and year 1 means that I only want to return the title attribute and the year attribute. So if I run that, this time it returns 3 documents, these 3 documents, but we only have these attributes returned to us. Note that we have this underscore ID, which is the primary key of each document. It will be returned by default. One important thing here to note is that we can either have ones in the projection, so you can either turn particular columns, particular attributes on in your results, return those particular attributes, or you can turn them off. So you can either have ones here or zeros here. So you can either return only those 2 or anything but those 2 attributes. The only exception is about the underscore ID attribute, which we can have a mix of those. So you can return the title attribute, the year attribute, and turn off the ID attribute. So in this way, it looks a bit nicer because we don't have to look at all those gibberish ID values. The title is, the order is different. So that's just the insertion order. Yeah. Oh. Okay. So an example of the fact that it's flexible. We don't have to follow a particular order for the attributes. The queries still work regardless of what the order is. Okay. So in MongoDB Compass, this projection will be available to us if we click on this more options here, and then you see projection. So simply we can type, let's say year 1, and then do title 1. And once we do that, you can see the documents returned to me are they contain much less information. All right, let's see a few more functions here. So sorting, we just add one other parameter here. So we had projection before, we had filter before, and here is sorting. So sorting based on a specific attribute. Here we're sorting based on runtime in ascending order. and then based on year in descending order. And remember that this only happens for identical values of runtime. So if we only have unique values for runtime, that second sorting doesn't do anything. So let's run that. You can see that the values, the documents, the return documents are sorted in ascending order based on the runtime. Okay? 98, 173, and 194 here. Okay, this is again something we had in SQL, the order by clause. And we also have this limit functionality. If you only want to return just a few documents, that's also doable. So you can do something like this. Limits only 5 documents, only return the title of those, and this is what we get. And finally, we have a few more functions to go over. So we have count documents to simply count how many documents are returned. This has its own method. We provide the filter inside of that. We don't use find in order to apply the filter. We just apply the filter right in the count documents. So here, 618 documents are returned for the year 2000. This is information that will be shown to you here. When you do your search, it will show you, for example, 3 of 3. That means that only 3 documents were returned. Okay. We also have the skip functionality. We can skip the first few documents, or the first however many documents that we like from our results. Again, these are just arguments to this find function over here. Let's run that. Okay. We also have this distinct function, which only returns unique values that exist in a field. So it doesn't return the entire document for which that has unique values in a certain field. It only returns distinct values that exist in a certain field, not the document. In order to return the entire document that contains unique values, we have to use aggregation pipelines, which is something that we're going to be learning about in the next lecture. Yes?
If we're connected to a remote database, are these happening in the remote database, or are these happening on our local computer?
Yes. So the query happens on the remote database, and only the results are going to be returned to you, the client. Yeah. So all of those principles, basically, that we have learned about relational databases, the server-side processing and everything like that, it all applies to non-relational databases as well. Okay, so that's the last thing we had here. Okay, let's take a few questions. We have still 5 minutes to go. Yes?
Kind of a follow-up. If we're working with really big data sets, and we're doing a machine learning project with something that we take off database, how would that work in terms of our code? Like, would we be mixing this code with Panda's code and trying to push that back into the server to do a calculation?
Right, exactly. So the question is, how, if we are training a machine learning model and the data comes from a database like this, how does that work? So you have your Python driver, and then you make a query to the database based on what you want to train your machine learning on, and then the database returns that data to your computer. You train your model up to a certain point to that, and then you might want to do your training in chunks. So you return the next set of data, and this is actually why you have a generator object. Return a bunch of documents, maybe train your model on that, and then return the next bunch of data, because there's a huge amount of data. You don't want to load everything onto your computer at once. This is basically how it works, yes. Yeah. Other questions? Oh, sorry. Yeah. Oh, okay. So the question is, our query is based on a specific match. So, for example, title equals to that, or the year equals to that. How can we do stuff like smaller values, smaller than this, values greater than this? We will learn about all of that in the next lecture. So about different kinds of operators, and also aggregation pipelines, which enable us to do much more complicated type of analytics on the data that we have. Okay, so I guess if there's no more questions, yes.
Just for the function like skin, you may already said it, but is that just based on what order documents were?
Yes, that's based on the insertion order if you don't provide any sorting function. If you do sort the documents, then it just skips the first view that you, yeah, right, yeah. All right, so this is it for today's lecture, everybody. I'll see you folks in the lab tomorrow. Thank you.